So he knows
so let me start the introduction. So thank you for joining this session of virtual seminars in economic theory. Today we have Ravid from Chicago, who is going to give a presentation on learning before trading on the inefficiency of ignoring free information. We are very pleased to have guest panelists, John Leahy and Benjamin Hebert. The format of these seminars is as follows. We have 60-minute presentation with times for interim questions from the panelists. This is followed by 15-minute session for questions and discussion. We request all attendees to keep your microphones muted during the talk. However, please post comments and questions in the chat. There will be an opportunity to ask questions live in the Q&A sessions at the end. This talk is recorded. And before I hand over to Doron, let me remind you that these seminars take place on Thursdays, 4 p.m. UK time. Next week, we have the last session before Christmas break by Chiara Margheria from Boston, signaling what you don't want. As usually, you can find more information on our website or by following us on Twitter. Thank you, Doron. The mic is yours.
Thank you for the wonderful introduction and for inviting me. And thank you, John and Ben, for joining. So this is a joint project with Anne-Catherine Rosler and Balázs Szentes. And the starting point for this project is that nowadays buyers can learn a lot of information about sellers and products, but in some cases they have to learn this information before they see the terms of trade. Think about getting your car fixed, for example. You can do a lot of research as to what might be wrong with your car, how much it usually costs to fix it, and look at reviews of various mechanics online. But to actually know how much it's going to cost to fix your car, you have to bring your car to the mechanic. Similarly, if you want to fix something or change something in your house, you can do research online as to how much it usually costs and look up contractors, but you have to bring the contractor over to get an estimate. Another example which seems to fit, but doesn't, I'm not an expert on it, let me say it that way, is over-the-counter corporate bonds. So if you want to get one of those bonds, you have to call a dealer. And it turns out, and this is a stylized fact, that if you call a dealer, ask about a corporate bond, hang up and call the dealer again for a second price quote, they'll give you a higher price than they gave you initially. That's because they learned something about your outside option. So in that kind of situation, if you want to learn anything about the firm whose bond you want to buy, you want to learn that information before you call the dealer in the first place. So what we want to do is we want to understand what does the need to learn product information before you see the price do to the terms of trade between the buyer and the seller. And we're going to do this in the following super stylized model. So we're going to have a single buyer and a single seller of an indivisible good. The buyer's valuation for the good is going to be distributed according to a nice distribution over 0, 1. So full support, absolutely continuous, and has strictly increasing virtual values. And the seller's value for the good is 0, and neither the buyer nor the seller start the game knowing the value of the good. The game begins with the seller and buyer acting simultaneously, with the seller setting a price and the buyer choosing which costly signal to acquire about her valuation. Then the buyer sees the price, sees her signal realization, and decides whether she wants to buy the product or not. Now, we're going to be interested in the world in which information is abundant, which we interpret to mean two things. First, information acquisition is going to be flexible, so the buyer can acquire any information that she wants. And second, we're going to focus on the case in which learning is almost free. Okay. So this is the kind of the player's structure, broad overview structure of the model. What I want to do now is give you just an overview of the results, and then I'll give a few more details about how we model things here. Okay. So we're going to be looking at sort of 3 cases of the model. The first case is when learning is absolutely free. In this case, it turns out that there are multiple equilibria, and the equilibrium outcomes are all Pareto ranked. Okay, so equilibria that give higher profit to the seller give also higher surplus to the buyer. And it turns out that the full information equilibrium is Pareto best. So the equilibrium in which the buyer learns her value and the seller uses the monopoly price against the buyer's valuation is the Pareto best equilibrium. The second case we're going to look at is one in which learning is costly. And there we'll see that the buyer's signal generates a unit elastic demand and that the seller randomizes over an interval of prices. The last case we'll look at is when costs are vanishing. So this is the limit of costly learning equilibria as the costs go to zero. And there we will get that equilibria converge, but they don't converge to the salient full information Pareto best equilibrium, but rather they converge to the Pareto worst among the free learning equilibria. Okay. So these are kind of the overview of the results. Now let me kind of give you a little bit of details about how we model things. So as I said, we're going to let the buyer use any signal that she wants in order to learn about her valuation. And the buyer's utility from trade is going to be quasi-linear. So if the buyer's valuation for the good is V and she buys the good at a price of P, then the buyer's utility is going to be V minus P. What this means is that the only statistic that the buyer cares about from her signal is her posterior mean valuation for the good given the signal. And so if learning more information is at all more costly for the buyer, it's going to be without loss for the buyer's signal to just be equal to this expected valuation. Okay. So we're going to normalize signals so that the signal realization is the buyer's posterior mean value for the good. And once you do this normalization, it's not too hard to see that both payoffs and trade outcomes are going to depend only on the marginal distribution of this signal. From the buyer's perspective, I kind of just talked about it, right? If the buyer's signal is S and she buys the good, then her expected utility will be S minus P. And so knowing the distribution of this S is enough for us in order to figure out when will the buyer trade and what will be her payoffs when she trades. As for the seller, what the seller cares about is the buyer's demand, which is the probability that the buyer purchases at any given price. In other words, it cares about the probability the buyer's signal realization is above any price, and that probability is summarized by the marginal distribution of the signal. So what we're going to do, and I should point out this is not new for us, this has been done in the literature in the past, is we're going to model the buyer's information acquisition by letting the buyer choose any CDF that could be a marginal distribution for some signal. So the buyer's sort of action set is going to be some subset of a set of I'll call calligraphic F, which is a set of all CDFs over 0, 1. And I'm going to equip the set of CDFs over 0, 1 with the L1 norm. It metrizes weak convergence, so there's nothing kind of, no exotic topologies introduced here. It's just I'm going to need a norm at some point, so I'm going to use that one. Okay. So what I want to do in the next few slides is to give you the description of the set of CDFs that can be part of a marginal of some signal. And the key concept for describing this set is a concept that we all learned in kindergarten. It is the concept of mean preserving spreads. So one CDF F is the mean preserving spread of another CDF F prime if and only if for every cutoff, the area to the left of that cutoff below F is larger than the corresponding area below F prime, where the two areas are equal if I were to choose a cutoff of 1. Okay. Now, why do mean preserving spreads matter for us? Well, it turns out that they characterize when is one signal more informative than another. Okay. So what do I mean by that? Well, one signal S is going to be more informative than a signal S prime if observing S is the same as observing S prime and an additional signal. So here's a fact that I probably should attribute to Blackwell, but some might say Rothschild-Stiglitz and maybe Strassen and a few others, so I'm just decided to not attribute it to anybody. And what this fact says is two things. First, one signal is more informative than another, only if the marginal of the more informative signal is a mean preserving spread of the marginal of the less informative signal. And second, if S attains, so if I have a signal whose marginal is a mean preserving spread of some CDF F, then I can find some other signal that is less informative than the one that I started with that attains F as its marginal. Okay. Now, these two facts mean that the set of CDFs that can arise as a marginal of a signal is the set of mean preserving contractions of the value distribution. Why is that? Well, observing your value is the most informative thing you can do. And if you observe your value, the marginal distribution of your signal is the value distribution. So point 1 here says that any other marginal has to be a mean preserving contraction of the value distribution. And observing your value is one signal you could use. And so point 2 tells me that any mean preserving contraction of the value distribution can be attained as a marginal of some signal. Okay. So what we're going to do is going to let the buyer use any CDF in the set. And I'm going to refer to these CDFs as signals. And I will say that one signal or one CDF is more informative than another, if and only if it's mean preserving spread of the other. Okay, so I'll use mean preserving spreads and informativeness kind of interchangeably depending on how well it works in my sentence. So this is going to be the buyer's action set. Now, every signal is in general going to come with a cost. And if you want to target some marginal F, there could be kind of many signal structures that will generate that marginal. And in fact, if you want to target an F, you don't even need to use a single signal structure. You can even mix across all kinds of signal structures. And as long as the average marginal is the F that you're targeting, that mixture would be a legitimate way to get your F. So what we would want to do is to assign every marginal with the cost of the cheapest randomization over signals that yields this marginal as its average.
Doron, can I ask a question here?
Sure.
So there's a paper by Kaplan and Dean in the context of rational inattention that talks about how in that setting, it is without loss of generality to think about information costs that are sort of ordered in the Blackwell sense and mixture feasible. It seems like what you're doing as someone who thinks about rational inattention is very close to that. Is that the right way to think about it or the wrong way to think about it?
No, that is exactly kind of the right way to think about it. I should say that I'm saying this kind of, but there's nothing really new in these arguments. Yeah, it's the same idea. And the same thing also shows up in, it's like this co-author paper, Denti, De Oliveira, and now I forget how to say the other two names, in JET. So this is the idea is that really if you have kind of this domain where that's the only thing you care about, then you can kind of think about the minimal expected cost on that domain, and you can just you write your costs that way. I apologize for people that I forget, how to pronounce their names. So, right, and that's the same thing. And indeed, like one of the properties that come out from Kaplan and Dean's paper and those other papers is that in this kind of environment, your costs are going to be convex without loss of generality. Okay. So we're going to assume that our costs are convex, and we're going to make two other assumptions. The first assumption is that our costs are differentiable, okay? Which means they can be locally approximated by an affine function. So first, what is an affine function here? Well, a cost would be affine if there's some Lipschitz function defined over the real line, such that the cost of every CDF is just the integral of this Lipschitz function. Okay. The reason we have Lipschitz is because of this L1 norm that's hanging around in the background. So that's what it means for a cost to be affine. What does it mean for it to be differentiable? Well, it means that for every F, I can find a little CF, Lipschitz function, such that the difference in costs between any other f prime and f equals to the difference in the integral of this Lipschitz function plus something that goes to 0 faster than the norm between these two CDFs. Okay. So I'll make this differentiability assumption. I'll point out that we don't really need the differentiability or so much smoothness per se. The reason I make this assumption is because these CFs, these Lipschitz functions, give us an object to which we can talk about the marginal costs of information. And that's where we really want to make our assumptions. Okay. And so that's what I kind of want to talk about next. So assumption that you might want to make, and in some sense has been pointed out, is without loss, is that costs are increasing in mean preserving spreads. In other words, if one CDF is more informative than another, then it's going to have higher costs. Now, Machina showed in a slightly different setting, but same idea works here, that if you have a Frischer differentiable function, it's going to be monotone in mean preserving spreads if and only if this Lipschitz function is always convex. So what we're going to assume is a little bit stronger than this. Well, it's stronger than this, to say it this way. We're going to assume that not only is your Lipschitz function is convex, but it's also strictly convex on the convex hull of the support of your signal. Okay. So, you know, the kind of, if you're trying to kind of get a sense as to what we're really assuming here, it is in some sense morally equivalent to assuming that the derivative of a strictly increasing function is strictly positive everywhere. Okay, saying that kind of the marginal cost of a mean preserving spread is always strictly positive. Okay? So it doesn't vanish, doesn't go to 0 too quickly. And I'll point out exactly where is the thing that we needed this assumption for. Okay. So these are going to be on assumptions on the cost function, and this is our model. Let me just kind of wrap up things. The seller can use any random price. So strategy for the seller is just a mixture over prices. A pure strategy for the buyer is just going to be one of these signals, mean preserving contraction of the value. Because the cost is convex, it turns out that it's without loss for us to focus on equilibria in which the buyer uses a pure strategy. So we'll just focus on those. The seller's profit is kind of what you'd expect. If the seller charges a price of P and the buyer uses a signal F, then the seller's profit is going to be P times the probability that the buyer's signal is above P. This minus here means that we're looking at the left limit of our CDF. And what this means is that we're assuming that the buyer is breaking ties in favor of the seller. Now, you can show that in equilibrium, this is without loss. And this is just kind of using standard kind of tricks, epsilon tricks. If the buyer was not breaking ties in favor of the seller could charge epsilon less than the price, and then you could take that epsilon to 0. So you can show that in equilibrium, this is always going to happen, but we're being lazy, so we're just going to assume it. The buyer's payoffs is what you'd expect. It's the buyer's expected payoffs from trade minus some parameter kappa times the cost of the signal, where the value of this kappa depends on the case we're looking at. In the free learning case, kappa will be 0. In the costly learning case, kappa will be strictly positive. And in the vanishing cost case, kappa will be vanishing to 0. Okay. Good. An equilibrium is one in which is a strategy profile in which the seller chooses prices to maximize profits, holding the buyer's signal fixed, and the buyer chooses signal to maximize utility, holding price distribution fixed.
Okay. Jaron?
Yes.
This might be a good time to ask questions. You've now finished the model, to ask questions about the important assumptions and that you have. Yeah. One question I had was, you motivated in the paper with comparing some buyers might have more information than other buyers, and informed traders might act different than others. You also talk about over-the-counter markets.
Yeah.
And much of the literature on over-the-counter markets considers other sorts of asymmetric information, like that the seller doesn't know how informed the buyer is.
Yeah.
And right now you have, people don't know their valuations, but the distribution F0 is common knowledge.
Yes.
How important is that assumption given the way the mixing is going to take place? Is that vital?
So that assumption is actually not super important to us. So what is important for us is that the seller would know the distribution of the buyer's signal. So basically that the seller kind of knows what F the buyer ends up using.
But if you don't know their distribution of F naught, do you know that they're prior? Can you know the distribution of the signal? Or how sensitive is the equilibrium to the prior? Would you get the same distribution of signals for multiple priors?
So you will see that at least when, the results themselves, of course, the limit, the thing you'll converge to and so on, depend on the value distribution. I can tell you that the kind of the classes of distributions that the buyer will be using when learning is costly will be pinned down kind of almost irrespective of the prior. The prior only gives you some
That's
sort of...
kind of what I thought, because you get this Pareto distribution, and that seems to be within certain parameters might be independent of the prior.
Yeah. Now, in terms of how we think of the seller learning this F, that's, we're kind of thinking of the same. This is like the standard way that you would think about, like, how do you learn the other player's equilibrium strategy? The broad idea is that this interaction maybe happens a lot. The seller sees, a lot of different buyers, and you kind of through the interaction you learn what the buyer's sort of effective valuation is. Now, you're right that you will not be able to learn what F naught is in that case, but maybe you can learn F. So, of course, like there's a little bit of a tension, especially if you think about like financial markets. Financial markets are dynamic, so by the time I interact with the next buyer, the valuation's already changed, and I'll never know their next. I'll never be able to do this learning, but we're kind of not the only ones that have this problem. But yeah, that's the idea.
My second question was, you couldn't have written this paper, could you, without the flexible learning technology? If you'd done a normal signal, normal prior structural model of learning,
yes,
you wouldn't be able to generate the indifference. I mean, you need this this flexible learning technology to generate your results. Is that correct?
Yes, yes. It's very much if information is constrained, there are some constraints that we can work with, but probably the constraints that you would naturally write down, let's say normal signals and so on, I admit I haven't worked it out, but I will not bet on those working, delivering or working for us. So yes,
well, you probably wouldn't get a Pareto distribution. Well, we'll get there, but I think these are key assumptions in the paper that we want to think about as we go on and see the results.
Yeah, that's true.
Can I ask a sort of related follow-up to that,
Sure.
Which is what John's question about the prior and then this comment about the flexible information technology made me think about is sort of the distinction between moral hazard and adverse selection, and how flexibility in moral hazard often gives sharp predictions about the nature of optimal contracts. So like, because I've sort of worked on that stuff, my natural inclination is to think about the H as sort of like a contract and the F as sort of like a action or a multidimensional action. And in that sense, this looks like a moral hazard problem with a very flexible action space, which often gives very sharp predictions about contracts, which in this case would be the H. So like Ming Yang's job market paper or my job market paper, we're both sort of touching on that. And then to John's point, if there was true adverse selection in the sense of, priors assigned by nature or something like that, that often looks very different than moral hazard, where the F is entirely a choice variable of one of the agents in question. Is that a reasonable way of mapping what you're doing, or is that sort of just left field, not really related?
No, it's very related. So you're right that in some sense here we're creating, there's a situation where selection is created using a moral hazard component, right? Because the seller does not observe the buyer's choice of information. One thing that's doesn't quite work with the moral hazard story is that the seller's contract, this H, is not observed by the buyer before she chooses her information. The buyer sort of knows what it is in equilibrium, but if the seller were to suddenly deviate, the buyer would not know that until after she learned the information.
So I guess what I wanted to ask is that important?
Yes.
Suppose that instead the game were structured such that the H was announced.
Yes. So,
but not the P, just the H.
Yeah. So that would be very important for us. Indeed, kind of, let's say, our motivation is to discuss cases where you sort of can't see the P ahead of time. It would, if that was the case, so the H is announced ahead of time, in our costless limit, you'll get the full information equilibrium. Okay, so we'll get what we said. I mean, it's not, I don't know, and that, in fact, that will be the unique equilibrium actually when learning is free too, or at least the unique equilibrium outcome. So it's really kind of important that the buyer cannot see the seller's announcement of the price distribution or the mechanism before she's choosing her signal structure.
Even though the equilibrium concept and the best reply involve knowing it in some sense.
Right, but I don't see, I know what the seller, I predict, it's like anticipating it, but not seeing it. So if the seller somehow decides to deviate and charge some left field price, I would not know that. I would not be best responding to that.
You get kind of to select your equilibrium if you get to announce first.
It's
the profit maximizing price, then they learn whether they're above, below, and there you're there in the full information.
Exactly. So that would be, that's the proof. So if you announce the price ahead of time, the buyer is going to learn and learning is free. Let's focus on that case. Then the buyer is going to learn exactly whether her value is above or below the price, and then the probability, the buyer's demand is going to, at every price.
Sorry, I don't want to derail this further, but I was thinking about announcing the H, not announcing the price.
Well, in full information, there's a single price. Let's get to the model. Let's get to the model. Let's show the result.
Yeah, but that's, you could announce a single price in principle if you announce an H. That's what, in that case, then but it's if you had a richer model where it wasn't like a, let's say, buyer seller, but an actual moral hazard where there's some action, cost, and so on, maybe then things could be different. That's in your job market paper. Okay, so we were talking about these truncated Paretos. So in case they're not familiar to you, and let me introduce them. These are a class of distributions that are very important for us, and they are important in this literature. So a truncated Pareto is parameterized by two numbers, a pi, which is going to be the bottom of the support of the distribution. The reason for using pi will become apparent in a few slides. And the second number is t, that is the top of the support of the distribution. And given a pi and a t, the pi t truncated Pareto generates a realization below S with a probability of 1 minus pi over S whenever S is in the support. And of course, the probability jumps up to 1 once you're going to S is above the support. I'm going to call a distribution a Pareto signal if it's both a truncated Pareto and a signal, so mean percent contraction of the value. And in case you're kind of not familiar with these distributions, I've drawn one representative member here, and the sort of squashed cumulative probability signal realization space. These distributions are 0 until pi, then they strictly increase in a strictly concave way all the way up to t, and then they jump up to 1, and they remain flat from there on. Okay, good. So the plan from here onwards is I'm going to do some preliminaries, which is probably just going to remind you things that you've seen before that allow you to sort of visualize the seller's profit maximization problem in this setting and the buyer's consumer surplus. And after doing these preliminaries, I'll just kind of go into and show you the results in each of these 3 cases and try to give you some idea for some of them, why do they hold. Okay. So let's maximize profits. So given a signal F, I want to find the seller's maximal profit, which I'll denote by pi subscript F, and the set of profit maximizing prices. That's going to be capital P of F. And I'll do it like in equal to 100. So I'm going to kind of look at the seller's isoprofit curves. And the space in which I'm going to look at isoprofit curves is the space that you would draw kind of a CDF in. So, pick any point in the space. The x coordinate of the point corresponds to like a price or a signalization. And the y coordinate corresponds to a probability that the buyer's signalization is below that price. So this means I can attach each point in this plane with a profit that is equal to the price, the x coordinate, times the probability the buyer's signal is above the price, so 1 minus the y coordinate. Once I can attach each point with the profit, I can ask what is the set of points that give you the same profit, and that will be all x, y's that in which y equals 1 minus pi over x. Now, this formula might look familiar to you, and one reason it might look familiar is because I showed it a few slides ago when I was talking about the truncated Pareto distributions, right? So this isoprofit curves for the seller for profit of pi turns out to be exactly the CDF of the pi truncated Pareto distribution when the truncation point is 1. So isoprofit curves are really just truncated Paretos with a truncation point of 1. The profit is kind of the bottom of the supported distribution, hence the pi. And profits are increasing as you go further down into the right, right? Because if you fix the rejection probability, higher prices correspond to higher profits. And if you fix the price, lower rejection probabilities correspond to higher profits. The set of feasible points for the seller is given by the buyer's CDF. And so given a CDF, what is the seller going to do? Well, the seller is going to choose the lowest isoprofit curve he can get away with. And that is the highest isoprofit curve that's everywhere below the buyer's signal. The intersection points of this isoprofit curve with the CDF is the set of profit maximizing prices. And because these isoprofit curves are always strictly increasing, any profit maximizing price must lie in the support of the buyer's signal. And the reason is that if it didn't lie in the support of the buyer's signal, the CDF of the buyer's signal will be flat to the right of it. And that means that the seller can attain a higher profit by increasing the price by a tiny bit. Okay. So let me kind of just record this last fact that I'll be using in this talk. And that is that the set of profit maximizing prices is always contained in the support of the CDF. Okay. So that was profit maximization. Let me now kind of just probably just remind you about how you would calculate consumer surplus graphically here. So fix some price P and some signal F. Then what is going to be the buyer's trade surplus? Well, if the buyer sees a signalization of S and the price is P and she buys the good, she's going to get S minus P in expectation. And so what that means is that the buyer's trade surplus is going to be the integral of this S minus P according to F, but of course only for signalizations that the buyer actually purchases, which are the ones in which S is above P. Do some integration by parts and you get that the buyer's trade surplus is just given by this expression here. And this is an expression that we kind of can see graphically. So we've drawn here one CDF that the buyer could have. And the 1 minus P corresponds to the area of the rectangle that is between the x-coordinate P and 1 and the y-coordinate 0 and 1. And the integral on the right corresponds to the area below the CDF to the right of P. And so the buyer's trade surplus is given just by the area that is to the right of P and above the CDF. Okay. Good. So I'm now done with preliminaries. Now let me talk about the different cases. So the first result I want to show you is the result that characterizes what happens when learning is costly in our model. So fix some costly learning equilibrium. Then the following two things are going to have to be true. First, the support of the seller's price mixture is going to be the same as the support of the buyer's signal, which is going to be convex. And second, the buyer is going to use a Pareto signal. Okay. So I want to try to convince you that this proposition is true. To do that, notice that really what I need to convince you is that point 1 here is true. And that is because point 1 implies that the seller is indifferent across charging all prices in the support of the buyer's signal, which means that on the support of F is identical to an isoprofit curve. That means that F has to be a truncated Pareto distribution. Okay. So really what I need to convince you is that point 1 here holds. So now it turns out that to do that, it's enough for me to show you or to convince you that if I have two distinct signal realizations in the support of F, then the seller must be charging a price strictly in between. Okay. Why is this true, or why is this enough? Let me say that. Well, remember that the seller only charges profit maximizing prices, and those are always in the support of F. And so if this claim in the middle of my slide is true, that means that between any two distinct signal realizations, there's another signal realizations. And therefore, because supports are closed, that means that the support of F is convex. And once I know the support of F is convex, this statement in the middle of the slide also means that the support of H contains a dense subset of the support of F. And then again, because supports are closed, that means that the support of H contains the support of F, but we know it's contained in the support of F. So the two must be the same. Okay. So this claim in the middle of the slide tells me that both the support of F is convex and that it's identical to the support of H. Now, proving this claim to you requires a little bit more time than what I have. So what I'm going to do is I'm going to prove a slightly easier claim. And that is that if I have two distinct signal realizations in support of F, and F has an atom at both of them, then the seller must be charging something strictly in between. Okay. And the broad idea of this argument will also be the way that you would prove the harder claim. So now I want to prove the claim at the bottom of the slide here to you, and I'm going to do this by contradiction. So suppose that I have an equilibrium when learning is costly, and in this equilibrium, there are two distinct signal realizations that F has an atom at, and that the seller does not charge anything in between. Okay. What I'll want to convince you is that the buyer benefits strictly from pooling X and Y together. Okay. And therefore, the buyer could not have possibly used this signal in equilibrium. So, right, so we're going to, what I've drawn here is one CDF that would satisfy kind of our assumption. So the CDF with some jump in X and in Y. And if the buyer were to kind of pool X and Y together, what you would get is a new CDF that is identical to the old one to the right of Y and to the left of X. And it now has like some atom between X and Y that has the feature that the total area that it is captured between these two CDFs in the interval xy adds up to 0. Okay, which in this drawing means that the area of the red rectangle is the same as the area of the blue rectangle. Okay, so let's show that the buyer is strictly better off with this red CDF, with this new CDF that pools X and Y together versus the old one. So first, observe that pooling X and Y here strictly reduces the informativeness of the buyer's signal and therefore reduces the buyer's learning costs. What about trade surplus? Well, let's go kind of like case by case for the prices. If the seller charges a price above Y, well, then the two CDFs are completely identical there, and so the area above them to the right of Y is the same. So the buyer's trade surplus is the same for those prices. What about prices below X? Well, the only hope for any kind of difference in trade surplus for those prices is the difference in the area here of the red rectangle and the blue rectangle. But those areas I just told you were the same, so there's no difference in trade surplus there. What about a price in between X and Y? Well, luckily those never happen, so I don't need to worry about them. So what did we get? Well, we get that this pooling of X and Y strictly lowers costs and doesn't cost the buyer anything in terms of trade surplus. So it's a strictly profitable deviation for the buyer. Okay. So this means that if in equilibrium, the buyer's signal assigns strictly positive probability to X and Y, then the seller must be charging something in between. Now, if you want to talk about realizations X and Y that don't have atoms, you can't quite use this argument because pooling X and Y together might not change your signal at all if either X or Y have probability 0. So instead, what we do is we pool together neighborhoods of X and Y, and we make these neighborhoods smaller and smaller. And this is where our assumption kicks in. Our assumption on the cost tell us that the cost gains or savings do not go to 0 too fast as we're shrinking these neighborhoods. Okay, so that's kind of where we need our assumption. Good. So that's what we are going to say about the costly learning equilibria.
So, Daron?
Yes.
So I have a hypothesis that the equilibrium will be independent of the prior. If you had one, suppose you start with one equilibrium. The first condition would be the second prior would have to be a mean preserving spread of the first, because you'd have to be able to create the same signal distribution from the new one. And the second sufficient condition would be that costs only depend on the marginal cost of information, not on the total amount learned, but just the marginal amount learned, which is a property of posterior separable cost functions.
Right. So
and I think that would also be necessary, but I think those would be the two things you would need for not having to know what the prior of the person is.
Right. So if the cost of a fixed
the cost only depends on the prior you end up with.
Yeah.
Posterior you end up with, and if all the priors are mean preserving spreads of each other, then you would have the equilibrium of the most informed person would apply to all the other people.
So I think you are right, but there is some things that's a little bit tricky that makes it hard for me to be 100% sure. So the thing is that we're working with this very reduced form way of thinking about information. And so the thing that's sort of a little bit, let's say if I had posterior separability, the thing I'm not 100% sure of is that when you are going to be, if you want to produce a particular marginal f, that the cost of that marginal will remain constant.
Not the cost, it's the marginal cost. It's at the end. The cost doesn't remain constant, but it's like the incentive to learn that last little bit of information is independent of price.
I see. So maybe, so that will probably.
I believe that's the case.
Yeah.
Daron,
So we can chat later, but I think those are the two things you need for prior independence.
I'll mention, related to John's point, that Mike Woodford and I have a sort of minor point in one of our papers showing that every cost function that's sort of sufficiently smooth in fact, is locally equivalent for small amounts of information to something posterior separable.
Right.
So I think my conjecture would be that, in fact, sort of combining the argument that John just gave with that fact, your limiting results would probably hold independent of the prior. That would be the conjecture.
At least local to for a small set of priors.
Yeah.
So I don't know.
Let
I think
me
actually for all.
Yeah,
but I sort of wanted to just ask a clarifying question on what you just showed. If the distribution of the prior was discrete, the proof you gave would have been enough.
So yeah, for our assumption of regularity of the prior is required only for it's not required for the costly learning parts. The parts where we're talking about the vanishing costs and the free learning parts, that it's required for that. Let me go back one thing to kind of connect things that you said. So Ben, your point, about the posterior separability. So one class of posterior separable cost functions that you could write are ones in which the cost of the cost of a posterior depends only on the posterior mean. That class of posterior separable cost functions is exactly the set of affine cost functions in our environment. Okay? Therefore, really what your point is exactly what we're doing is that we are assuming that our cost function is locally the same as a posterior separable cost function that is and so it's exactly kind of the same sort of idea. I would say we don't need that smoothness. As I said, we can kind of just there's weaker assumptions we can make that are in the paper, but those are much uglier than this. But yeah, no, you're right. The point that you were making with Mike it's kind of what we're basically doing.
Got it. Okay, thank you. Obviously, this helps me a lot. I'm not sure if it helps anyone else, but it helps me understand.
If you don't understand, then the chances of others is extremely reduced. So good. So this is kind of what our result about the costly learning case. I want to now talk about a result for the free learning case. Here, I'm not going to have time to prove the result to you. But what I do want to do is to present it to you and kind of show you what it says and get a feel for it. And to introduce this result for you, I need to kind of introduce two new pieces of notation. The first is this p bar of pi. So for any profit pi between 0 and the highest profit the seller can get when the buyer learns perfectly, this pi fv, I can define p bar of pi to be the highest price that would attain a profit of pi if the buyer were to learn perfectly. Okay, so so you can think, suppose the buyer were to learn perfectly, give me a profit pi that the seller can get. For each such profit, I can find the set of prices that would generate that profit. Take the highest price, that's your p bar of pi. Okay. The second notation that I need is pi lower bar, which is the seller's min-max profit when the minimum is taken over signal structures and the maximum is taken over price distributions. Okay. So our theorem for the free learning case characterizes the set of free learning equilibrium payoff pairs. In particular, it says that a profit pi and a buyer utility u is attainable in a free learning equilibrium if and only if pi is between pi lower bar and pi fv, and the buyer's utility is her utility if the seller charges p bar of pi, which the seller will in equilibrium, and the buyer learns perfectly, which in most equilibria the buyer will not. Okay. So this is our theorem. We have actually now the tools to kind of think about this theorem graphically. So what I've done here is drawn the CDF of a uniform value distribution over 0, 1, which satisfies our assumptions. And what the theorem is saying is that any profit between pi lower bar, the min-max profit, and pi FV is attainable, and only profits there. And given the seller's profit, I can find the buyer's utility by drawing the pi isoprofit curve and finding the intersection of this isoprofit curve with the value distribution. This intersection is this p bar of pi. And then look at the buyer surplus when the seller charges p bar of pi and the buyer uses FV. Okay? And so that's kind of the area above the value distribution to the right of this p bar of pi. Now, once we can kind of draw these little pictures, we can ask ourselves, well, what would happen to the buyer's utility as I move across equilibria in a way that increases the seller's profits? So, let's start from the lowest possible profit, look at the buyer's surplus, increase profit a little bit, increase it a bit more. You can see that kind of the buyer's surplus is increasing with the seller's profit. And this turns out to be because the p bar of pi is decreasing with pi. Okay. So we get here this corollary. So it turns out that this kind of ranking in which increasing the seller's profits increases the buyer surplus is not an artifact of the uniform distributions. It holds for any value distribution that satisfies our assumption, the regularity assumption. And so we get the corollary that all the free learning equilibria are Pareto ranked. Any equilibrium that generates the full information outcome is Pareto best. And any equilibrium in which the buyer ends up min-maxing the seller is Pareto worst. Okay. Going back to your comment, Ben, about like discrete value prior distributions, this is, this corollary will not work with discrete value distributions because those cannot be regular. If I have time, I can talk a little bit at the end about what happens with non-regular value distributions. Yes.
Jeroen?
Yes.
There seems to be a strong incentive on the seller's part to get the buyer to learn. So like just asking somebody comes into your mechanic, you used that example earlier, somebody comes into your store. I mean, you want to ask them a few questions and then, like give them some answers. Yeah, ask them questions, take the answers, and then reply and try to get their V. If you could ask questions, I guess the only thing that would happen would be the profit maximizing price, right? I guess there may be cost to questions as well, but there's really is an incentive to have a conversation.
Well, I guess so there's definitely incentive to reveal information, and I think that would be the I don't know if you had this experience in mechanics and contractors. They often, when they can, they take you, they show you, they
yeah.
So yeah, so if
that seems to all be trying to reduce these equilibria in some sense.
Yeah, so you're right. So as long as they can credibly reveal information, any information they can credibly reveal, they will try. I will say that if they cannot, if it's cheap talk, then they will not generally be able to convey. I mean, they can. There's some information you can convey, but it's a lot harder.
Yeah.
So I mean, this.
Now, if they weren't credible, is there any way for them to reveal information to get both better off?
So that is actually a good question if they are not credible. So I think, you can definitely
we all know mechanics that aren't credible, right?
Huh?
There are mechanics out there who are not credible.
Yeah, I think I know a few, unfortunately. And yeah, so so there is a way for them to reveal information. And I think that, let's say if the buyer had no information, I could say that that's probably like always bad for them. But if the buyer has some fixed information, I admit that I don't know whether there is an equilibrium which the seller reveals information, charges some price that depends on the information they revealed, that is better than what the buyer came in with. So yeah.
Can I just interrupt here and remind you of the time? We have about 5 minutes left.
Okay. So let me kind of quickly go to the last result that we have. We'll see how fast I can say it, and then see if I can, convince you of it completely, or I'm going to leave you with potential limbo about the, or big thing you have to swallow for it. So the last result that I have is about what happens when learning costs vanish. And to introduce this result here, I need to tell you something from my brilliant co-author's previous paper. They do a whole bunch of other things there, and I can talk about that maybe at the end. But one thing that's very important for you to know from what they do is that they show that there is a unique Pareto signal that attains the seller's min-max profit. Okay. So given this fact, our main theorem in this paper is that if you take any sequence of costly learning equilibria in which costs vanish, then this sequence is going to converge to the seller charging P bar of pi lower bar, and the buyer using the min-max Pareto signal. And this limit is a free learning equilibrium in which the seller attains his min-max profit and is therefore Pareto worst. Okay. So let me give you a broad sketch of the proof. Start with the sequence of vanishing cost equilibria. First, observe that this sequence lives in a compact space because both the set of CDFs over 0, 1 is compact, and the set of mean preserving contractions of any distribution is compact. So really, the sequence is just a union of converging subsequences. So it's enough for me to show you that if I had a convergent sequence, then that sequence would attain the limit that I said as its limit. Okay. So suppose that I have a convergent sequence of vanishing cost equilibria. Now the proof is going to follow from 3 facts. The first fact is that the equilibrium correspondence is closed. So that means that the limit of vanishing cost equilibria is a free learning equilibrium. That's a fact that's easy to believe, but turns out you actually need to prove some stuff here. The second fact is that the Pareto signal set is closed. That comes from the fact that the set of truncated Pareto distributions is closed, and the set of signals, or mean preserving contractions of the value, is closed. And third, and this is kind of the big kind of thing you would have to swallow, given that I don't have time to show it, is that if I have a free learning equilibrium in which the buyer is using a Pareto signal, then that free learning equilibrium has to be the one that is specified. Now, roughly speaking, this comes from the fact that this min-max Pareto signal turns out to be the most informative Pareto signal in terms of mean preserving spreads that there is. And so the buyer can always deviate. If she was using another Pareto signal, the buyer could always deviate to this min-max one and strictly benefit in equilibrium. Okay. So once we have these 3 facts, it's not too hard to string them together into the proof, right? So the first fact tells me that the limit that I get is a free learning equilibrium. The second fact, combined with the fact that the buyer, when learning is costly, always uses Pareto signals, tells me that in the limit, the buyer signal is also Pareto. And then the third fact tells me, well, I know that my limit is a free learning equilibrium in which the buyer is using a Pareto signal. Therefore, it must be this min-max bad free learning equilibrium. Okay. Yeah. So let me kind of just recap. So what did we see? When learning is free, all equilibria were Pareto ranked. Full information was Pareto best, and the buyer using a Pareto signal is Pareto worst. When learning is costly, the buyer uses a Pareto signal and the seller randomizes over its support. And when learning costs vanish, we got the Pareto worst free learning equilibrium. And I have some extensions, generalizations we can talk about, some literature stuff, but I'm kind of running out of time, so let me just leave it here.
Thank you very much. Great talk. So we are now moving to the Q&A sessions and discussion sessions. Let me start with our panelists if they have anything to add or ask at this stage, and then we'll move to the audience.
I've asked everything during the talk.
Okay.
I did want to circle back to that one issue about maybe the connection or lack thereof to the moral hazard, and how, you know, if you could interpret this as contracting. So I must confess, I still am sort of reaching the conclusion that it looks to me a lot like a buyer choosing an F ex ante before the seller must propose a contract, and then the states are realized. And the contract space, obviously because this is like a goods allocation problem, is sort of restricted relative to like a continuous payoff. But so one result that I had was that the order of the actions doesn't matter when you have sufficiently flexible actions, at least provided that you're willing to do things like restrict to proper equilibria. Mm-hmm. And basically the intuition is just that, you know, the best reply conditions that you have, like that the H has to be the best reply to the F, and the F has to be the best reply to the H, are sort of like the, you know, H was picked after the F, right? So, and that the F was picked knowing that there would be a correspondence, you know, of optimal H's given the F.
Yeah.
So my conjecture is that it is in fact sort of like that.
So as long as the seller, so let me kind of, so now you're talking about the version of the model in which the buyer were to select her signal structure before the seller announces the, let's say the contract. And a contract here is without, you could have done a contract or a mechanism rather than a price, as you pointed out. So the buyer chooses a signal before the seller chooses the contract. Now, if the buyer's signal choice is private, then it doesn't matter. The game forms are equivalent.
Exactly.
Right. If the buyer's, and so indeed, I think even when we wrote the paper, we wrote it in without being simultaneous move. We wrote it as buyer chooses signal structure first, but the seller doesn't see it, and then the seller chooses price.
Well, and that is the motivation that you gave, right? Is that you want to do the research before you show up at the mechanic shop.
Right, right. And so you're completely right that then those two models are equivalent. I only present them in simultaneous move because my experience has been that people, if I say kind of the order, they kind of, sometimes people forget the, or I say it too fast, like the word private, and so it's going to miss. So saying simultaneous avoids confusion.
Well, but I guess the point that I'm raising is that when we think about, if we flip the order, like the natural interpretation for your setting, since this is research before the mechanic shop, is choosing the F first, and then the mechanic chooses the H. We've convinced ourselves, I think, that that's equivalent to the simultaneous setting where they just both choose at the same time. But my claim is that it's also equivalent to the setting where the H gets chosen before the F. And that third option is the one that looks like moral hazard, in the sense that the H there looks like a contract, mm-hmm. and the F looks like an action. And so I think this analogy might be interesting as a way of thinking about what you're doing. That is that the ordering of the events may be irrelevant.
So let me kind of react. So as long, of course, if the seller's price distribution is private, then the order will not matter.
Exactly.
If the seller's price distribution is public, so it's not, maybe not the realized price, but the price distribution, which again doesn't matter because you can always choose a unique price atom, unit atom, then the model does change. It could be that, and the reason is again because then the buyer can adjust her information to what the seller is offering. Now, one key word that you were talking about, like about order of moves, which might matter, and it's kind of hard exactly to do it here, because like infinite strategy space, but you can probably sort of make it work somehow, is the word proper equilibrium. So suppose that I took my model and now, no, so in some sense you can view what we did here, right? As an equilibrium selection thing. We said, well, when learning is free, the whole bunch of equilibria out there, and we're saying if learning is kind of costly, you're going to get this kind of bad one, even if the costs are very, very small. So the free learning equilibrium is approximately right. Now, of course, there are other kinds of refinements you might have wanted to do. One refinement that you would have wanted to do instead is, let's say, maybe the seller's price trembles, and that kind of looks like a proper equilibrium. And if you did that, then the equilibrium that's selected, if you sort of did just tremble, so no costly learning, then the equilibrium that's selected is the free learning equilibrium outcome. Okay, and so which is exactly the same outcome that you have gotten if the seller was publicly announcing her contract at the beginning of the game. Now, of course, if you're and the reason is that really what is happening here is that the buyer is choosing a signal structure that is weakly dominated by free learning, and the buyer can do that because there are prices that the seller is sort of not really charging in equilibrium. Therefore, if the seller had like a tremble, then the buyer would learn the information that's relevant to that when learning is free. So, you know, kind of like there's a question of which refinement works. And of course, if you were to take limits in different orders and different speeds, then you kind of can select either of those equilibria. So you're sort of right that there would have been an order equivalence under some trembles of the seller, but that order equivalence would have kind of moved us away from what we have here if you weren't taking the costs of learning at some point somewhere to zero in the right way. So, yes.
Oh, that's a great answer. It sounds very interesting and might be in some future something worth thinking a little more about.
Yeah. Thank you.
Okay. Are there any other questions from the audience, please? This is the time when we can interject and ask.
I had a question, but Angel also has a question. I don't know who wants to go.
Yeah, I have a question that is almost answered with the previous answer. Okay, but still, I mean, let me insist on this to see whether you have new insights to provide about my specific aspects. You know, I mean, my question is about that you assume that the cost for the seller is zero. Okay, which is basically you assume that it's common knowledge that there are gains from trade.
Mm-hmm.
So that I guess that's for technical convenience. I wonder whether it has any implication, and it also seems to matter a lot for the result of convergence. I mean, certainly it is the case when there's asymmetric information about the cost for the seller. No, it's exactly the argument you just gave about trembling the price of the seller. So I was wondering whether you have some insights to provide us about this question.
Right. So let me there are two, I didn't have time to talk about extensions and variations. So there are kind of two of those that are relevant to your question that we're dealing with. And thank you for asking this, because that gives me an excuse to talk about it. So one thing you might be worried, as you said, is that we're assuming cost is zero or the value of the good to the seller is zero. You can ask, what if it was a deterministic number that's not zero? The answer is, if that number is sufficiently small, so below the prior mean, everything remains the same, but I now need to define an uglier class of distributions that are not quite truncated Pareto, but they're kind of something you're shifting things by the cost. And this is these like C-shifted truncated Paretos that are here. If the cost is above the prior mean, turns out that in the costless limit, you get that the buyer learns, so first you get the buyer learns nothing when learning is costly, and no trade is going to occur in the vanishing cost limit. Okay, so trade is completely going to break down in this environment. And the reason is that in any equilibrium in which the buyer buys when learning is costly, the buyer, the proposition that I showed, the proposition 1 when learning costly, has to still hold. So in the sense that the seller must be randomizing over an interval, and the buyer's signal there, is that interval, and has to be therefore a C-shifted truncated Pareto. However, if you look at this family of C-shifted truncated Paretos, you can see that it's always supported to the right of the cost. And so if the cost is the prior mean or above, there is at most one signal structure, one distribution that can be this, can satisfy these conditions. That is just an atom at the prior mean, which means that the buyer learns nothing. Okay, so when learning is costly, that means even if there is trade, the buyer learns nothing. Of course, if there is no trade, the buyer will not learn anything. And now, as you take costs to zero, the equilibria are going to converge to a free learning equilibrium. But they must be converging to a free learning equilibrium in which the buyer doesn't learn anything. And the only one like that, given our assumptions on the value, is the one in which the seller charges the price of 1 and the buyer doesn't learn. Okay. So that's kind of an answer to one part of your question, is that if costs are sufficiently high, then our model actually says things will break down. And if the costs are sufficiently low, same kind of things hold up. Another thing that you kind of talked about, and that's a more advanced maybe version of the question, is what would happen if, let's say, the costs of the seller were kind of private. Okay, so the seller had some private, let's say, private value for the good or some private cost, and it's supported with a full support distribution over 0, 1. Then it turns out the broad takeaway of our model still hold, as long as you assume that the value distribution is regular. But there are some, of course, a lot of more technical details that are uglier and take longer to prove. And there are some small changes. But what you can show is that the free learning equilibria are still Pareto ranked, and full information is still Pareto best. And the key thing that that gives it is that it turns out that all free learning equilibria can be parameterized by the price that the zero cost seller is going to charge, and so that price is going to be P bar of the zero seller cost, zero seller's profit. And if the seller charges that price, the buyer's CDF above that price is going to be identical to the value distribution. Okay, so at this, the seller is going to, and so in an free learning equilibrium, the price distribution is going to be contained in an interval that is between P bar of pi and 1. Okay, so it's going to be that interval. And then when learning is costly, something similar to my proposition holds, but for only sufficiently low costs. And then as learning costs vanish, you can do a very similar argument that lies behind the truncated Pareto version, but you need a little bit more work to do it. But you can show that then you're going to have to converge to the free learning equilibrium in which the free learning, the free cost seller charges the P bar of lower pi, so that same price that he charges in our bad free learning equilibrium. And any equilibrium like that is the one that is Pareto worst. Okay. I know this might not have been that super clear because I'm talking without a lot of the details. Some of the stuff is summarized in a paragraph in the paper, and there's now an appendix that if you're brave enough to read, you can read it, and then you can also tell me if there are any, tell us if there are any mistakes or something.
All right, great. I think we have reached the quarter past, so we are going to hang out after the official finish of the presentation. But meanwhile, let me thank Doron for the great presentation, and John and Benjamin for participation, active participation. Thank you very much, and everyone else for presence. We'll see each other next week, and then we'll take a Christmas break